inverter, current source inverter, and AC voltage controller. So you see that what we have done as of now is that AC voltage controller, AC voltage controller, then voltage source inverter and current source inverter. These three things we have done yesterday class itself. Okay, so today's class we'll see how we will use this cycloconverter. I hope you know what it does. It converts one AC to another AC, but this time it just vary the frequency. Okay, it varies the frequency that step up cycle converter, step down cycle converter. So brief circuit diagram I will draw here. So where do you give the cycloconverter is you give the cycloconverter to the stator of the induction motor. So now the stator may be a star connected or delta connected. Let me take the delta connected. Okay. So once again, the cycloconverters are several types. Half wave, full wave, okay, and bridge one is there, midpoint one is there, step up cycloconverter, step down cycloconverter. Different cycloconverters are there. So I will take one type of that I will take and I will just explain it. Okay, so I hope I hope we can easily understand this thing that because already we have gone through the cycloconverter operation, so it is not so tough to understand. Okay, then okay, this one is positive group. I hope you know what is a positive group, what is a negative group in case of the cycloconverter. Okay, so whereas these three are negative group. And now this is connected here. Similarly, we have see every phase we have six thyristors. Okay, then you have another group. So then you have third phase. Every phase you have positive group and negative group. Okay, so okay, this is the cycloconverter. And I hope you can understand this thing that the three black lines which I have done, this is three-phase supply. Okay, so it is a three-phase supply. This one is three-phase supply. This three-phase supply. Then this three-phase supply goes to the stator of the induction motor through a cycloconverter. Okay, this cycloconverter, based on the switching style that we have studied in case of the cycloconverter, you get different waveforms here, different frequency waveforms here. Okay, so then I hope you remember this. Now I hope you know this thing that eh, as these are thyristors. Okay, so there is a type of commutation you require, sometimes forced commutation, sometimes natural commutation. Okay, it depends upon which type of cycle converter it is. Okay, step up cycle converter or step down cycle converter. Okay, so if it is step down cycle converter, I hope remember it is a natural commutation, whereas for the step up cycle converter it is a forced commutation. It depends that whether you want to increase the frequency or whether you want to decrease the frequency, and you have the relationship with the frequency and you have the relationship with the frequency and the voltage and all these things. Okay, uh, then we'll draw. Then we'll draw the block diagram. We'll draw the block diagram. Okay, so now you see here. Yeah, please observe this block diagram here. So this block diagram is very same as the block diagram which we have studied for the PWM inverter. Here also you have the PWM inverter. Okay, now where is the scope for the cycloconverter here? That is the question. Where is the scope here? After this PWM inverter, you can put if you want, or simply instead of having this block, see why I have drawn this thing is that only intention is that this block diagram using the cycloconverter and the block diagram using the PWM inverter, they both are same. Okay, except here there is a small change in the power circuit. I told you already this is called the power circuit. Power circuit in the sense the circuit which gives the power to the induction motor, and remaining all these things you call it as a control circuit. This entire thing, this blue color circle, okay, this entire thing it is a control circuit. So only what you find out here is that in case of the cycloconverter, the only difference you will find out is that in the power circuit, that for the cycloconverter you need AC, so you need AC as the input. So how you get the AC here is that instead of having all this, you directly take the AC which is available three phase AC supply. But in case of the PW inverter, what you do there, please recall that what you did there, you simply have converted this somewhere you have the AC supply is there. So you convert AC to DC using the rectifier. Then that DC onwards we will take here. That DC onwards we will take here. So then you have the large inductance here. Then it depends now once again whether is a voltage source inverter or current source inverter. We will go ahead like that. Whereas in case of the cycloconverter, what you do is that you have the AC circuit here. Then that AC directly you take here in the cycloconverter box. Something like this. I will modify this. I will just modify this here. That this is a cycloconverter. So you got the three phase AC here. Okay, then that goes to the induction motor. Nothing else. So that directly goes to the induction motor here. Okay, whereas you get the feedbacks here. Obviously you get the feedbacks here. The frequency will get the feedback here. Okay, the frequency will get the feedback here. So and remaining everything is same. This entire thing you see here, what exactly you are doing here? Now you are taking the speed, you are taking the speed as the feedback. Then you compare with the reference speed here. This is the actual speed, this is the reference speed. Then you have the speed controller. Then based upon that you will have the slip regulator. Okay, so here we get the slip value. Okay, from the slip value, already I have told you this thing that the slip speed n sns plus nr is nothing but ns. This already we have seen. Then based on ns, your ns can be written as 120 f by p. So you'll get the frequency here, f. So you'll get the frequency here based upon this ns only. So then you have this voltage, you take the feedback here. You see here I have taken v as the feedback here, voltage. Okay, so then that voltage will be compared with the reference voltage. Now how you are generating the reference voltage is that you are generating the reference voltage from the flux control box. So now this flux control box is very important. Even we have seen in the last classes also that the voltage, this everyone know this equation. So from this equation, there is a relationship between the voltage and the flux. So based upon that, it generates the reference voltage. How it generates the reference voltage is that, okay, you see here yourself. For example, see in the cycloconverter, either you increase the frequency or decrease the frequency. This is what exactly you do in the cycloconverter. Okay, so for example, you decrease the frequency of this graph. You recall. Okay, this is V, this is F. So there is a point here, that is a rated value. Till rated values, the voltage and frequency both are proportional. That you reduce the frequency, voltage also will be reduced. You increase the frequency, voltage also will be increased till this point. But beyond that, even though you increase the frequency, you maintain the voltage constant. So this This logic is given in this flux control box. This logic that when you have to keep the voltage constant and when you have to change proportionally. So that is given in this. So based upon that, it generates the voltage. So that reference voltage will be compared with the actual voltage. Then the power circuit will get changed here. Then the power circuit will get changed here. So now the firing pulses you will get here automatically. Okay. So this is about the closed loop control. See, the closed loop control is very same as the previous one itself, except what is the difference you will find out here is that there you have from AC to DC, then DC, then AC, then after that you have once again AC. Okay, so this case it is different. Now there are some PWM techniques which you have already studied. That what are the PWM techniques you have studied is that. So I hope I will just start PWM. I want to just tell you one thing. So see, in the previous block diagram, there is one M is there. What is this M here? M is the modulation index, which I have defined last class itself that it is a modulation index M is equal to amplitude of carrier wave or carrier signal divided by amplitude of reference wave or reference signal. This I have defined. So if you recall this PWM technique, you have this ramp signal. The ramp signal here you have like this. Then the carrier may be see several types. The carrier may be, for example, the carrier may be a DC value like this, or the carrier wave may be a sinusoidal like this. It depends on. Once again, we have different techniques. Sinusoidal PWM is there, and just conventional PWM is there. Multiple PWM techniques are there. So different techniques are there. But the main purpose of this is that to generate the pulses. So just comparing the carrier wave with the reference wave, you get the pulses based upon which is higher, which is lower. Based upon these differences, you will get yourself that um, the pulses will be generated. Okay, so and we have some advantage over this PWM techniques is that we can control the harmonics a little bit here using if you follow, for example, sinusoidal PWM technique is there, conventional PWM technique is there. In case of the sinusoidal PWM technique, now the harmonics are better controlled compared with the conventional PWM technique. So the PWM techniques, different types of PWM techniques are being discovered, are being invented, being defined. Okay, all these their main job is that to control the harmonics, the main thing. Okay, so this entire thing now which we have studied as of now, that is stator control. Now that's over. This topic is over. That we just summarize that stator control. So what we did in the stator control as of now, you see. So stator control in the sense the induction motor which you have. Okay, the induction motor which you have something like this. Okay. So this is your stator. I hope you know the operation of this induction motor. So this is your stator, and this is stator. Whereas this is rotor. Okay. So you give the supply here. You are giving the supply here. Okay. Generally, there's a single excited machine. It is. So you give the supply here. So now, as of now, what we studied is that see when I change the variables here, stator side, this is stator side. When I change the variable here, V and F, these are the two variables, voltage and frequency. How how the torque and speed of this entire induction motor has changed. So what are the methods that I vary from this side? Okay, either on the stator side you may have AC voltage controller, AC voltage controller, or you may have voltage source inverter, or you may have current source inverter, or you may have cycloconverter. See, all these things you connect on the stator side. Okay, all these things. So that the reason that all these things we call it as stator control methods, stator side control methods. Now we will go, we will go. Now from now onwards, we'll discuss about the rotor side. So how can I do something on the rotor side so that we can control the induction motor? Because I hope you might have remembered this thing that to control the induction motor, either you go for the stator side control or you go for the rotor side control also. Okay, in either case you can control the um, performance or you can control the properties of the induction motor. Okay, so one I will tell you the basic or the rotor side, the very standard method is that controlling the rotor resistance. Controlling the rotor resistance will definitely control this. We have seen. How do we know this thing that yeah? So I don't want to write the equation here right now, but I will just show here something which is necessary. Okay, so the equations, I hope you remember the torque equation. We have solved some numerical problems also. So you can go through that yourself. This one. So this is your stator and this yellow color is the rotor. Okay, so now this time what you do is now don't change any kind of supply to the stator. You just give the three-phase supply which is available, which is coming from the distributed station. Okay, then what you do here is that you vary the rotor resistance. I hope you remember this thing that two types of rotors are there: squirrel cage and slip ring induction motor. So slip ring rotor, in the slip ring rotor you have the option. What is the option? You have the option to connect that rotor to an external circuit. Okay, this is the option you have left in case of your slip ring rotor. So that option will take care here. And then you see here that you have it's a three phase here. So you connect a resistor here. Every phase you connect a resistor. Okay, and then obviously what you do once again, anyhow, see here it's not a constant resistance, it's a variable resistance. Okay, then only you can vary the resistance here. So then you join all these things, you short all these things at one point. You short all these things at one point. Anyhow, you have to close the circuit here. Then see here, by varying these values, these are, so you can take three phase resistor. I hope you know what is a three phase resistor. That when you vary that uh, the terminals, when you vary this something like that, you might have seen in the laboratory what is a three phase resistor, three phase resistor. So just like your inductor is there, so you rotate that wheel, then R value will definitely change. Okay, this is the logic we have been following. Okay, so okay, so now you see, and just now I will draw the I will draw the graph here. I will draw the graph which represents I will draw the graph that has torque speed characteristics. Okay, just it's a repetition only. I'm just showing that there is a method, there is a method using which we can control the induction motor from the rotor side. That's what I'm trying to show. Just I'm just you can say like this that it is just revision of the previous topics. Yeah, nothing is there. So slip I will take here. So here 0, I will take it as 1. So up to this, there's a motoring condition. Up to motoring condition we'll discuss. Beyond that we'll see. Okay. So what is the graph if you recall? So something like this, you'll get the graph here. Yeah, that's it. So this point is T max. I hope you know this thing. Whereas this point is TST, the starting torque. This is starting torque. Okay. Okay, starting torque. And now you see one more thing that I hope if you might have remember this thing that what is the thing you might have remembered is that this at this point there's a derivation already. You might have remember this thing that I will write here. S is equal to, or otherwise you just check yourself, R2 by X2. You'll find out this thing. Okay, this is R2 by X2. So at this slip value, you'll get the maximum torque. Okay, and before that and after that, it is less than the maximum. This you know. And now what you do here is that now you'll see the logic here. What is the logic behind is that so what is the logic behind is that by changing now what exactly you are doing now is here in the rotor side is that you insert some extra resistance in the rotor side, you vary and you include this in the rotor resistance. So when you include this, what do you find out? In the slip here, this R2 is there, that is in the numerator. So that is a rotor resistance. So when you include some extra resistance here, then that resistance R2 will rise. R2 will rise. So if R2 is rising, whereas X2 remains constant, you are not changing X2, only R2 you are changing, then your slip value will increase. So slip value will increase in the sense the slip at which maximum torque occurs, it increases. It increases in the sense you see here, this is the slip, this is the slip axis. So slip axis, this is the increasing side. So it means this point which is here, this point which is here, it will move towards right side. Definitely it will move to why it will move because S is equal to R2 by X2. You are R2 you are increasing by adding some extra resistance. So numerator increases. Then the entire slip will increase. So slip increase in the sense this point will shift towards right side. So the maximum torque now will come here when you increase the resistance. So I will just join this. Now you see when you do this like this, when you do this, when you do this, what did you find out here? You see here, you just draw the graph. When you do this, see here earlier you see the starting torque was here. Now the starting torque has increased. You see here, the starting torque jumps here, and also your slip at maximum torque at which it occurs, it also shifts right side. So two things have happened here. One thing is that the maximum torque, when you increase the resistance, see what exactly you are doing is now you are increasing the resistance. When you increase the resistance, okay, two things we have observed. What are the two things we have observed is that what are the two things we have observed that the slip at which maximum torque is increased, so it moves right side. Similarly, the starting torque goes up. So it means what? When you increase the resistance in the rotor, then the starting torque will increase. So anyhow, what exactly you are controlling the here? You are controlling the induction motor characteristics by changing the rotor resistance. Okay, there's a logic here using this logic. Okay, so I hope you know you got all these things already. Okay, then not a big thing to understand. Okay, then we will do one thing. We will We'll solve a numerical problem now. Okay, using this just information. Okay, so a three-phase 440 volt 6 pole 50 Hz delta connected slip ring induction motor has a rotor resistance of 0.3 ohm, 0.3 ohm, and leakage reactance of leakage reactance of 1 ohm per phase refer to stator. So the values he has given are refer to stator. When driving a fan load, when driving a fan load, when driving a fan load, it runs at full load. It runs at full load, full load at 3% slip. Okay. What resistance must be inserted in the rotor circuit? Must be inserted in the circuit, in the rotor circuit to obtain a speed of 800 rpm. rpm. So he has given something neglect stator impedance and parameters. The stator to rotor turns ratio is rotor turns ratio is 2.2. So this is the question he has given. Okay, now we'll have to okay, now you see the question first we'll see a three-phase 440 volt 6 pole 50 Hz. Okay, delta connected slip ring induction motor has rotor resistance of. So he has given the data regarding the induction motor, that is the rated values and the resistances also. Okay, refer to these things. Okay, then when driving a fan load, when driving a fan load, okay, it runs at full load at 3% slip. So when you are driving a fan load, it runs at full load at So the induction motor is connected to a fan. What resistance must be inserted in the rotor circuit to obtain a speed of 800 rpm? Okay. Now that's the question he is asking. So the data which he has given here. Okay, the data which he has given. Okay, so based on the data, we'll go ahead, and some things he has given that he has neglected the stator impedance and the stator side parameters he has neglected by somehow. Okay, then we will take like that only. Okay, we'll take like that only. So then then we'll go ahead with that. So how to go ahead? I hope you know this thing that just I will copy this picture here. Yeah, this picture I think is a suitable picture to us now, right now. So please see here now. He said that what he said is that this rotor, you are connecting. Where exactly you are connecting here? You are connecting this to a fan. That's important. You are connecting. So you are coupling this to a fan. So you are coupling this to a fan. This is what he said. Okay. So your rotor is coupled to the fan. Now he said that what resistance R, see here, what resist, where is R here? Here is R. What resistance R should be there in the rotor circuit so that the fan runs at 800 rpm? That is the question. So you have to make this to run at 800 rpm. So what resistance you will add here? Okay. So then I hope you remember this thing that few important things which I would like to say here is that first of all, he said one more thing that so you know the operation, what is operation here? Now by giving the supply here, the rotor develops a torque, and that torque, okay, will be, so you can call this torque as te, electromagnetic torque, and this you can call it as tl. So I hope you know this thing that at equilibrium te is equal tl. T is equal TL in the sense initially when you turn on the supply, so the fan is not running initially because the fan is at rest. So when the fan is at rest, okay, so the, I hope you know this thing that the in case of the fan, in case of, so then you need this equation. In case of the fan, what is the relationship between load torque and its speed? This is important. How do you know this thing? Okay, how do you know this thing that what is the relationship between load torque and the speed? It is a relationship k n square. You may find out even in the net also what is the load torque of a fan. So how it is, or you can see this thing that what is the relationship between torque and speed for a fan. Then definitely I'm sure that you may get this equation. So whichever equation you get here, we will have to use that equation as the load torque. That's what I said. So this is the load torque. So load torque has a relationship with the speed. So when speed is zero, that is during starting of the induction motor or during starting of the fan, you turn on the fan. As soon as you turn on the fan, that is during starting, the speed of the rotor and also the speed of the fan is zero. So when the speed of the rotor, speed of the fan is zero, load torque is zero. Whereas what is the electromagnetic torque? Immediately electromagnetic torque has developed something. So this TE now greater than TL when during starting. During starting, TE greater than TL. Then what do you observe? When T is greater than TL, then the rotor will get accelerated. So the electromagnetic torque is more than the load torque in the sense the rotor will get accelerated. So the speed of the rotor will increase. So it will increase and increase till the load torque, because when the rotor starts accelerating, n increases. So when n increases, TL also increases. So TE remains there itself, whereas TL started increasing. So when TL started increasing, okay, then what do you find out? At one stage, TE and TL both are become same. Okay, see here, during starting you turn on the supply. When you turn on the supply, what you observe is that at that time initially the fan is at rest, so the load torque is zero, whereas the electromagnetic torque has already developed. Now we would like to write the equation for the electromagnetic torque. You recall that the basic equation of the electromagnetic torque. So I will write that equation here, okay, for the purpose. So right here, so See, if there is any mistake, you can correct that later also, no problem. I'm just writing these equations directly from the sources available. So R2 dash by S whole divided by whole divided by R2 dash by S whole square plus X2 dash square. Okay. In there any change you can tell me also, no problem. So this is the electromagnetic torque, whereas the low torque is this equation. TL is equal to Kn square. So immediately your electromagnetic torque will be developed, and its value is using this equation. You can find out this value. Using this equation, you can find out this value. Now the low torque is zero. So then what do you find out? So the rotor starts accelerating. So when the rotor starts acceleration, fan also move. Fan also will move. Why? Because both are coupled mechanically. So n value increases. When n value increases, T also increases. So when TL increases, one stage it will reach that T is equal to TL. So at that stage, you call it as equilibrium. Okay, at that stage what do you find out is that no acceleration, no deceleration will be there. So no acceleration, no deceleration will be there. So it runs with a constant speed. Okay, that is the thing. So now what you do here is that simple thing, what exactly you do here is that, okay, so he said clearly this thing that I want to make he wants to make this thing that what he wants to make this thing that he wants to make the speed of the fan to be 800 rpm. So for that purpose, what is the R you will add here? That is the thing. So what is the R you will add here is that, okay. So before that, first we'll do one thing. Um, First of all, we will find out the full load torque. See here, when driving a fan load, it runs at a full load at 3% slip. So we'll do one thing. First, we'll find out the full load torque here. Okay, we'll find out the full load torque here. So how do you find out the full load torque here? So at full load, he has given some slip. Please see there, 3% slip. So we'll substitute that here 3%. Now, what are the unknowns here? I will write here omega ms is the synchronous speed. So how do you find out the synchronous speed? I hope you know this thing that omega ms is equal to 2 pi ns by 60. What is ns? Ns is equal to 120 f by p. So in the problem he has given the frequency, the problem he has given the number of poles, everything he has given. Okay. And so what is n he has given in the problem? You see somewhere. I think this data he has not given. No, we have to find out ourselves. F is equal how much? 50, then 6 poles. So 1000 rpm. So you will get ns 1000 rpm. Substitute 1000 here, then you will get the answer approximately 104.72. Yes. So F is 50, P is 6. Then you will get 1000. So 1000 that you 1000 you substitute here, then you will get the answer 1. So you got omega ms. Then what is V here? V is the, see, it's a delta connected, he said. So what is the voltage he has given in the problem? The voltage he has given in the problem is that 440 volts. So he has given 440. So you directly put the 440 there. Why? Because in the delta connection, line voltage, phase voltage, both are same. So you don't need to worry which voltage is that. So directly you write 440 here. Then after that, R2 dash he has given in the problem. How much he has given? You just see somewhere he has given as, yeah, 0.3. Slip is 3%. In the sense slip is equal to 0.03. So slip is equal to 0.03. That also you know. Then what else you don't know here? X2 dash. I think X2 dash also he has given, yeah, 1 ohm. So then you substitute everything here, then you will get the electromagnetic torque. So I would like to write directly Te is equal, when you substitute there, you will get the approximate answer 548 Newton meter. This is the answer you will get. So now what you do here is that, see here, now TL is equal to Kn square. I would like to change this n as nr because the speed of the fan is coupled to the your fan is coupled to the rotor. So rotor speed is same as the speed of the fan. Okay, and we will take that there are no rotation losses. Okay, because he has not mentioned anything regarding the rotation losses. So we'll take like that. Then What else you find out here is that, what else you find out here? So when I take this n arc, so TL is equal k, TL is equal k into nr square. So what is nr here? Nr is the rotor speed. So we'll do one thing that, what we'll do one thing is that, so at rated values, how do you find out nr? You can easily find out nr here. How to find out that? Um, there is a relationship is there for the slip. Nr, sorry, ns, ns minus nr by ns is equal to slip. This you know, slip you know, ns you know. Then you can find out nr. So what is the value of nr here? You will get whatever may be the value you will get here. So simply substitute the nr here. Then what about the load torque? I told you already that in equilibrium condition, both are same. Both are same. Okay. So anyhow, we'll find out nr first of all. It's better that 1000. Okay. So we'll write here. We'll find out nr. Then only we will get some things. So 0.03 is equal to 1000 minus nr by ns. That is 1000 once again. So what is the answer you will get here? Answer you will get here. So 30, 1000 minus 30. So 970. So I think it is 970 only. So 970. So you will get nr is equal to 970. So this answer we got 970. So this is at full load. Please remember now, this is at full load. So what you will get here is that, so this is at full load. It's very important. So this 970 rpm is at full load. So at this time, what you do now? Anyhow, this fan will you have to equate this. Both are at equilibrium. Both are same. Then TL is equal to TE. So how much we got? 548. So 548 is equal to K into 970 whole square. So why we are doing all these things is that we want to find out the K value. That is the only intention. Nothing else is there here. We did not enter into the actual problem yet. So you will get here 970 to 548. So you got approximately 5.82 into 10 power minus 4. This is the value of K we got. Okay. Once we got the value of K, now we will jump to the question now. Now what is the question he is asking? That if the fan speed, is equal to 800 rpm, if the fan speed is equal to 800 rpm, yeah, yeah. Please answer. Is the screen visible? See, it got disconnected here. Please answer. Is the screen visible here? Anyone? Okay, thank you. So see now. See now, so we will jump to the actual question. What is the actual question is that at this fan speed, he is asking what is the value of R you will insert. That's the question. So now you do one thing that at this fan speed, first we will find out what is the slip. What is the slip you will find out at this fan speed? That ns minus nr. So 1000 minus this fan speed is nothing but nr. So 800 divided by 1000. What you will get here? 0.2. We'll get 0.2. So slip we find out. Then what's next now? What's next is that we will simply use the same equation which we have used. So that is T is equal to TL. Anyhow, see whatever you do at the end at equilibrium, T should be equal to TL. That's the logic. So now T, what is the formula you got here? 3 by omega ms into V square into, now this time R2 dash plus R. I will write. Why I am writing R is that now you are inserting some extra resistance. When you insert some extra resistance, that comes in series with the rotor resistance. Okay. So divided by R2 dash plus R by S whole square plus X2 dash whole square. So this is the electromagnetic torque, and this should be equal to the load torque. It should be equal to load torque. Now, what is the load torque? Now we'll recall. Load torque is equal to K into NR square. What is K? We find out 5.82 into 10 power minus 4 into NR square. What is NR this time? 800 RPM. So 800 square. Okay. So multiply with 2 times you have to multiply. Then you will get 372. So approximately you will get 3. So this is 372. So we will put 372 here. And now what are the unknowns here? You see the entire equation here. What are the unknowns here? Now everything is except only one unknown is there. What is that? R. The S value 0.2 we find out. V omega ms everything so except R is left. So when you solve this equation, so please solve this equation yourself, because now it's a quadratic equation you will get. So the R value you will get approximately, see, two answers you will get. If it is a quadratic equation, you are getting two answers. So when we got two answers, we find out that the answers which we got are two answers. I will tell 2.656 ohm. The other answer is minus 0.286 ohm. So mathematically it may be possible, but practically this negative resistance is not possible. So we will strike out here. So this is the answer. So solving this equation, you will get this answer. Okay.